Alright, this is lesson 6.6, and we're going to be talking about something called Hopital's rule. You can do a quick Google search on this guy's name, Hopital, and see what he was famous for. He probably was famous for this rule that he created. When do we use this? Well, we're going back to the idea of limits. And I want you to know that some limits can't be found using algebraic methods. We learned back in Unit 1 that you can just do direct substitution for some of them, and sometimes it produces some weird, what we call indeterminate forms. The one you've seen in Unit 1 was this one, 0 over 0. Why do we call this an indeterminate form? Because we really don't know which one to do first. Do we divide by 0? That's a problem. Or do we do 0 over 0? Like, is this simplified to like a fraction of 1? Like, what happens? It's indeterminate because we don't know which of the zeros, either the numerator or the denominator, really does dominate. Another indeterminate form is if you have infinity over infinity, whether it be plus or minus in both the numerator or the denominator. When you see these types of results after doing direct substitution of a limit, then we can use Hopital's rule to help you actually find the limit. And Hopital's rule is this: if when you do direct substitution you get those indeterminate forms, then what he said was that the limit of the original rational function is really just equal to the limit of the derivative of the top divided by the derivative of the bottom. So it's the derivative of the numerator divided by the derivative of the denominator, and then you apply the limit. So the key thing here is this: it has to be a rational function, so you must write this in fractional form. Okay, if it's not in fractional form, you can't use Hopital's rule. So let's look at some examples here. Example number 1. Remember, the idea is to do direct substitution first. So when I do, I get infinity over e to the infinity. Well, that's just infinity over infinity, and that's one of those indeterminate forms. So I'll say it's the infinity over infinity form. So therefore I'll apply Hopital's rule. So then I'll actually say, let's use Hopital's rule since we have the infinity over infinity form. And therefore now we have the limit as x approaches to infinity. The derivative of x, the numerator is just 1. The derivative of e to the x is just e to the x. And now if I were to plug in the value of infinity, e to infinity, of course, that's really, really big, and therefore the result here is 0. So the limit of the original rational function is 0. By the way, on AP exams, you need to do some sort of quotation of using Hopital's rule or saying something like that. Okay. On my unit test, you'll need to do the same thing. So let's look at number 2. Once again, we're going to apply infinity. So in this case, oh, look at that. Infinity over infinity again. Okay. I'm just going to be lazy and just going to say use Hopital's rule. Okay. And once again, if I were to now use the rule, I'd like you to take the derivative of the numerator, which is just, of course, e to the x. The derivative of the denominator is just 1. So now when I plug it in, I get e to the infinity, which is really just infinity. So the answer here is infinity. Some books, some teachers think that just means does not exist. I prefer infinity. Okay. Try number 3. Once again, direct substitution is what you do first. So 0 over e to the 0. Well, that's just 0 over 1, so this is just 0. No need here to do Hopital's rule, because the result is just 0. And that's not an indeterminate form. This is actually a number. We're done. Let's move on. Turning the page, got a few more for you to try. So once again, the idea is to do direct substitution. This is 0 to the left, so if I put this in, that's e to the, I guess, 0 to the left. Pretty much that's 0. This is 0 to the left. The numerator just becomes 1. 1 divided by 0 to the left. Remember, that's the same thing as like divided by negative 0.00000001, so that becomes really just negative infinity. Okay. Once again, no L'Hopital's rule required here because my result was not in the form of 0 over 0 or infinity over infinity. Number 5. Once again, plug in the point or the x value of 0. 3 minus 3 e to the 0 over 0. That's 3 minus 3 is 0 over 0. Ah, here we have the indeterminate form, 0 over 0. So now let's use L'Hopital's rule. And therefore, if I ask you to now take the derivative of the numerator, derivative of 3 is just nothing. Derivative of negative 3 e to the 3x, well, negative 3 is a constant. E to the 3x is just e to the 3x, but then you have, oops, what did I just press there? But then you have an extra 3 that's involved. And the derivative of x is just 1 in the denominator. So this just becomes the limit of x approach to 0 of negative 9 e to the 3x over 1. Plugging in this, that just gives me the answer of negative 9 over 1 or negative 9. So that's the resulting limit. Okay. Numero 6. If you were to do this one, negative infinity squared, plugging that in, that just becomes infinity, because infinity squared is just infinity. And e to the negative infinity, well, that's 0. Now, this is an indeterminate form, but it's not the form that we want for L'Hopital's rule. We need to have a fraction. So what can we do? Well, one of the things we can do here is just rewrite this. So I haven't done L'Hopital's rule yet, but I'm just going to rewrite this as x squared divided by e to the negative x. So e to the x in the numerator just becomes e to the negative x in the denominator. Why is this helpful? Because once again, if I plug in now infinity, I get infinity at the top. E to the negative infinity is e to the infinity, that's infinity at the bottom. Now we have one of those indeterminate forms that allows us to use L'Hopital's rule. So I'll say since infinity over infinity occurred, now we can use L'Hopital's rule. And L'Hopital's rule once again states that we just take the limit as x approaches to negative infinity, but we take the derivative of the numerator, so that's 2x, and the derivative of the denominator, that's e to the negative x with a negative in front. Plugging in now negative infinity, I get negative 2 times infinity, that's just negative infinity, and then the negative of e to the infinity, that's infinity. Whoa, 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 what's this? Another infinity over infinity? Guess what? You got it. Let's use L'Hopital's rule again. Whoa. I'm running out of space. The derivative of 2x is just 2. And the derivative of negative e to the negative x, well, that's just, I think, positive e to the negative x. And so now if I were to plug in negative infinity and get 2 over infinity, and that equals to 0. So all this work to show that this limit equals to 0. Okay. Number 7. Whoa. Natural log. If I were to plug in the numbers, I get 1 over 0 minus 1 over 0. That's like infinity minus infinity. Kind of cool, but still indeterminate. Problem though, it's not a fraction. So once again, how can we rewrite this as a fraction or a rational function? Because you have 2 fractions, perhaps we can find the common denominator. And if we were to do this, I hope you see that the numerator is just x minus 1 for the left fraction, and the numerator becomes natural log of x on the right hand side, or the right hand fraction. Now if you were to plug in 1 minus 1 minus natural log of x, I believe that's just 1 minus 1 minus natural log of 1. That's just 0 on the top. And on the bottom, natural log of 1 is 0 times 0. Here's our 0 over 0. Knowing that 0 over 0, we can now use L'Hopital's rule. And now please take the derivative of the numerator. The derivative of x is 1. The derivative of 1 is 0. The derivative of ln x is 1 over x. And in the denominator, I see two things multiplied together. That's right, product rule. A prime b plus b prime a. A prime b plus b prime a. You can sing the whatever. Okay, so a prime b. So a prime will be 1 over x times x minus 1 plus a, which is natural log of x, times b prime, which is just 1. No need to simplify unless you want to. Okay. But let's see what we get in this time. We will put in 1. So that's 0. Uh-oh, I have a feeling this is also 0 over 0. Nasty, nasty, nasty. Do it again. Brutal. Limit x approach to 1. Do we have to do this again? Just notice something here. See how that x in the denominator? I'm actually going to do something first before taking the L'Hopital's rule again. What if I were to multiply both the top and the bottom by x, just to make things a little bit nicer? I'd now get x minus 1, I believe, in the numerator. And then now in the denominator, x times 1 over x, that's just 1, so that's x minus 1 plus x times ln x. I think this looks much nicer. Okay. I know when I plug in 1, I still get 0, though, over 0. But I think I can now do L'Hopital's rule one more time. Running out of space. L'Hopital's rule one more time. I'll just do it over here. So the limit as x approaches to 1, once again, the derivative of the numerator, that's 1. The derivative of the denominator, that's 1. And then, product rule again. A prime b plus b prime a. So that's 1 over x times x. And that's just equal to 1. So I'm just going to erase this and put this as 1. And now if I were to plug in 1, I think you have the lovely answer 1/2. So notice in the last two examples, sometimes you have to use L'Hopital's rule not once, but twice, or maybe even 3 times. I believe on the AP exam, I've never seen it done more than 3 times. Alright. Let's do example 8. So once again, 8, you plug in -1, and I believe you get 0 over 0. Now, I told you this one, let's do it without L'Hopital's rule. You're like, what? Yeah, do it without. What does that mean? Remember when you had 0, 0, what did we do back in Unit 1? This was a question where you needed to kind of factor and find the factor of x plus 1 in the numerator. And I hope you remember how we got that. We'll factor out the 2. Oh, lovely difference of squares. And there we have it. Those divide out. And you're left with this limit. And then you plug it in. I'll just plug it in. Negative 1 minus 1 is negative 2, so that's negative 4. Remember how we did that? Yeah. Well, now I want to do the same thing with number 9 and show you once again using L'Hopital's rule then how we can get the same answer. So just like in number 8, it's the same question. You got 0 over 0. So now I'll just take the derivative. The derivative of 2x squared is just 4x. The derivative of negative 2 is 0. The derivative of x plus 1 is just 1. And now if I plug in negative 1, notice the answer is also negative 4. Cool. Alright. There are other forms that are indeterminate. You know that? Yeah, so let's take a look at what we have. If I were to plug in for number 10, infinity for x. 1 plus 1 over infinity, that's just about 1. So this is the same thing as 1 to the infinity. And this, we don't know which one dominates, so this is also an indeterminate form. Right, it's ambiguous. 1 to the power of infinity. 1 times 1 times 1. Is it 1, or is it so much infinity, it's so big that we don't know? Hard to say. Next one here, this becomes, I guess, 0 to the power 0. Also, once again, not too sure which one dominates, so indeterminate as well. For number 12, that's infinity to 1 over infinity. Well, that's just infinity to the power 0. Once again, not too sure what dominates, so indeterminate as well. And then finally, for this one, sine of 0 is just 0. 1 over 0, and this is to the positive, that's infinity. This one, however, is not indeterminate because this actually does equal 0. 0 times 0 times 0 times 0, still going to be 0. Not indeterminate. So, I'd like us to take a look at 14, which is exactly the same as 10. And 15, which is exactly the same as 12. If these are indeterminate forms, the question is, can you actually find the limit? And the answer, of course, is yes. And we're going to use something to help us out. When we have powers with variables, I'd like us to use this trick. I'd like you to let y be equal to that limit. And then whenever we want to try to bring down the exponents, you guessed it, let's take the natural log of that whole thing. And with natural log, this right-hand side just becomes x times natural log of 1 plus 1 over x. Now, if we left it like this and plugged it in infinity, we get the form infinity times 0. That's not what I want because I want to use L'Hopital's rule. So this is where I'm going to ask you to try to write a fraction, or create a fraction. And the easiest way to do that is to keep the ln on the numerator and remove the x and write it as 1 over x in the denominator. Because now if you were to plug in infinity, you get now 0, and 1 over infinity is 0. That's an indeterminate form that allows us to use now L'Hopital's rule. And of course, L'Hopital's rule states that we can just take the derivative of the numerator. So the derivative of ln is what? 1 over that. So 1 over 1 plus 1 over x times the derivative of 1 over x. Now the derivative of 1 over x, That's x to the negative 1, so the derivative is negative 1 over x squared. That's the new numerator. The derivative of 1 over x, you just told me, is just negative 1 over x squared. That's the new denominator. Notice then that these just divide out, so you're left with the limit of x approach to infinity of 1 over 1 plus 1 over x. And if I plug in infinity, that becomes 1 over 1 plus 0, or just 1. Now what you've just told me then is that the limit is not 1, but the natural log of y is 1. Okay? Because remember, all this is equal to the natural log of y. So once again, you've just told me the natural log of y equals 1, not y. I want to find y though. So to get rid of the natural log, we'll take e to both sides. And so therefore, y is equal to e to the power of 1. And y, once again, was my original function of the limit as x approached to infinity of 1 plus 1 over x to the power x. And so the answer here is it's e. And by the way, we saw this in pre-Calc 12 when I tried to explain to you what e was going to be. Alright, you try 15 because it's similar to what I just did here. Okay? Go ahead. Let y equals to the limit and begin your process of solving. Check back with me here after you're done. Okay? You should be able to do this now. Boo, wrong form. Ugh. So once again, take natural log 1 over x, limit 1 over x, natural log of x. Now if I plug this in, this becomes infinity over infinity. Yay, that's the indeterminate form I'm looking for. Now I can apply Hopital's rule. Natural log of x is the numerator, so that is 1 over x. 1 over x is, the x is in the denominator, so that's just 1. So in this case, you just get 0 over 1, which is 0. So therefore, natural log of y equals 0. E both sides. So so y is just equal to 1. Or the limit of x approaches infinity of x to the 1 over x equals to 1. Alright. Whew! Still with me so far? Alright, 2 more questions to go, and then we're done. Sometimes limits can be evaluated quickly using the concept of relative growth rates, because remember, you're just comparing which one grows, which one gets bigger faster. So before we do number 17, I'd like you to rank the following in order of rate of growth as x approaches infinity. Okay, so when x is really big, how do things grow from slowest to fastest? Got the function x squared. And by the way, if you have a picture, you can help you out, right? Y equals to 1. Y equals to x. Right? Natural log. Power 10. Whee! E to the x. Whee! Alright, so which one's the slowest? I hope you said y equals to 1. Because that's like no growth. It's flat line. The next one, probably ln x, right? Graph seems to be flattening out, but much more than 1. I'd say the third one is just the linear power of x. And then as the power of x increases, of course, you're getting to infinity faster. And then I'd say x to the power 10. And finally, e to the power x. That's probably the fastest growing one. Okay? Now, why is this helpful? Because now I can use this concept of relative growth rates to actually evaluate the following limits. So, notice I have here limit as x approaches infinity. That's cool. Natural log of x in the numerator, and then e to the x plus x cubed. So they're both going to infinity, right? All these things are going to infinity. But look, the top goes to infinity slowly, right? Whereas the bottom here, that's really fast, right? Fast plus x cubed. So something slowly, something pretty fast. Well, slow divided by fast. Yes, both of them are infinity, but we can say which one grows to infinity faster. It's the denominator. So that's bigger, or it dominates. So it's like having infinity in the denominator. So kind of like that. And therefore the answer is 0. Okay. 18, you can think, oh, e to the x is fast. This is slow. So the answer is infinity. But you made one major mistake. And the major mistake is the limit here says x approach to 0. But remember, I can only use relative growth rates when x approaches infinity. So relative growth rates for this do not apply, because you're taking the limit as x approaches 0 and not the limit as x approaches to infinity. Don't get tricked. That's it for Unit 6. We're done.